Thank you very much for inviting me to give this series of lectures. It's absolutely great to be here, and it's great to see that many young people who are at the beginning, on the first day, they are still very intensely attentive. We'll see what happens in the coming days. So I don't exactly remember my title, but it's about random walks and diffusions with long memory and scaling limits for these. So the point is about what is Brownian motion in the end, after we scale and all that. As most of you have a background in mathematics. Anyone has some background in physics in the audience? I don't mean degree in physics, but interest, and not so many. Not so many. So if I ask you what is Brownian motion, what will you tell me? What is Brownian motion in the view of the audience, or a typical member of the audience? Okay, if you don't answer, I tell you what you would answer. Brownian motion in the mathematical culture means a stochastic process, right? Don't be bored, you know it. I will denote it like that. Say in RD, it's a random process with some defining properties. And the defining properties, I will not, of course, I assume most of you know, but maybe not all. So so independent and stationary and Gaussian increments, which means that if I write down WTJ minus WTJ minus 1, with J goes from 1 to n, and these are non-overlapping intervals, so T naught is 0 less than T1 less than Tn, which is finite. Then these are independent random variables, independent Gaussian random variables with expected value, let's say 0. I don't repeat. 0, it could be some constant times t, but let's take it 0. And with the variance squared be sigma squared times t j minus, let me just write delta tj. You know well this, right? So this is a Gaussian process with independent and stationary increments like that. You could give other axioms which are equivalent, but let me stick to this one. And there is one more very, very important character, which is pathwise continuity. Continuous almost surely. And this defines the process. That's how you know Brownian motion. Now, I will call this object Brownian motion within quotes. Because, yes, within quotes, because this is a model mathematicians invented for a phenomenon, a physical phenomenon, which takes its name from Robert Brown and comes actually from physics. Now, before going to physics, let me just give you all know the story of this. So, I mean, of the mathematical object, started at the beginning of the 20th century with the work of Bachelier, who was the first person who, in France, I don't have to emphasize it that much, the first person who wrote a most interesting study about his PhD thesis, actually, about this object, not naming it like that, not knowing about the physical problem. Actually, Bachelier was not interested in physics whatsoever. He was interested in gambling and in money, in financial market. Okay, not called like that, but that was his main interest. About the same time, it was Einstein. So let me just write down the name. In 1901, Einstein, 1905, and Smoluchowski, 1906. These are the three names to be mentioned for the persons who came up with the idea that this must be an interesting object. These two guys came from physics, actually were physicists. And as I told you, Bachelier has no interest whatsoever in physics, as far as I know. But you see, it was not formulated. If you look at Einstein's paper dated 19, you essentially find these axioms. Of course, not with these names. He doesn't use these terms, but you find this axiom. If you look at Smoluchowski's paper, it's very interesting mathematically. It's maybe a bit richer mathematically than Einstein's paper. It's about the same object. Now, but they too, they knew that okay, before I go to bed, okay, you know the mathematical story then, that in 1922, what's his first name? Wiener. What's his first name? Norbert Wiener gave the first construction. This is an interesting thing. You may not be, okay, another question which potentially I could ask. What is the construction of this object? Construction of this object is absolutely non-trivial. That such an object exists, up to that is not difficult. Accepting this one is absolutely non-trivial that such an object exists. So it was constructed, so the existence was proved by Norbert Wiener in 1922, and this is not the paper you think about, which was published jointly with Paley in 1933, where he constructs with Fourier transforms. There was an earlier construction by Norbert Wiener. This is just an amount of mathematical history, which is very interesting. But Fourier analysis is not used at all. It's an abstract function analytic construction. Very interesting. And Wiener and Paul Levy and so on, you know all the story. And it became absolutely the most important object of probability, certainly. But I would say in mathematics is a gold mine of mathematics altogether. But this is what I call that. Because Brownian motion without the quotes is a physical phenomenon. It's the phenomenon of okay, I won't be that strict now in formulation. So it's something like this. We have a random motion, call it xt. This is the motion of a particle interacting with some background, which could be a gas of other particles with which it collides. It could be, it collides with the other particle and moves under the action of the other particles and Newtonian dynamics. It could be, on another scale, a motion in interacting with some environment in the background, which is random. This more general formulation of that. So anyway, the problem is that this is a random motion. Okay, I don't write it down, interacting with background, and the randomness may come from the initial conditions, and some elements of stochasticity in the dynamics, but not necessarily. It's defined in terms of some physical, more basic physical object. It doesn't have at all properties like independent increments. And what you are interested in is proving that in the large scale, I will give you examples, and my lectures will be about this type of problem. And the main goal, I was not very definite now, I just gave general thing. And the main goal would be to prove that in a scaling limit, say take x capital T divide by square root of capital T, because you know from probability 1, 2, and 3 that's the scaling of this object, that this random variable converges to a normal. Converges to a normal with zero expectation and some variance where in d dimension. Or if you are more ambitious, then you want to, this is about one point, one fixed time point of that. But if you are more ambitious, you could say, take this process, and prove that as a process, it converges to Brownian, let me call this the Wiener process, Brownian motion between quotes, to the Wiener process. And the difficulty comes from the fact that, Of course, we know if this had independent and stationary increments like ordinary random walk, it's not a trivial fact, but it's a theorem, and we know it's good mathematics. But in true life, that's not the case. So the difficulty, usually the difficulty comes from, okay, the main difficulty always comes from memory. That this process you are looking at has long memory. It's not the case that it's built up by independent steps, right? And there are beautiful theorems in traditional probability saying that if you have a sequence of random variables, a stationary sequence of random variables, not independent, but satisfying some sort of mixing condition, and these are very well concretely and explicitly given mathematical terms, some mixing of the sigma algebras, faraway sigma algebras, then convergence to Brownian motion or convergence to standard normal or to a normal will follow. But these theorems are beautiful mathematics, of course, these mixing type of things. But whenever you have a concrete problem coming from physics, you will never be, okay, maybe that's too much to say, but I've never been able to use them. Because life is not like that these are beautiful mathematical conditions, that alpha mixing, rho mixing, gamma mixing, whatever, it's not easy to check. Okay, so here are some examples. The zeros example in my lecture, by the way, I have to give some disclaimers about my lecture notes, even more than Asaf said. I didn't even type most of my lecture notes. I gave handwritten lecture notes, partly and partly papers, and the lectures will be a combination of these, and later I will, after the lectures are finished, I will write up the lecture notes. At least that's my plan. Now, the zeros example is the baby example, and it's a trivial one. Let me not go to it. Namely, that if you have simple independent, simple symmetric random walk, then this problem is well understood for simple. So if this guy is simple symmetric random walk, say in continuous time, then this is, the first one actually goes back to de Moivre, to the 18th century, the central limit theorem. And if you want to prove convergence of the process, you look up the papers of Donsker and actually further back in time, Markatz and Paul Erdős about the invariance principle, and you find it. But the point, the interesting examples are not these. And let me give you some interesting examples. And let me start with the most difficult one, about which I will have very, very little, if anything, to say. But just for you to know that that's a holy grail. That's a great thing. Example one is the gas of particles. Indeed, imagine that infinitely extending in Rd, you have billiard balls floating around. This will be modeling particles which are placed randomly in a Poissonian way with the constraint of non-overlapping, which is a non-trivial constraint, but at least at low density, this measure is okay. So place these billiard balls, assign to each particle independent Gaussian velocities. These are the velocities of different lengths, because these are independent Gaussian velocities. This is back, you go back to classical statistical physics, to Maxwell's law. It's easy to convince yourself that this is a good choice. And now tag one of the particles and let the system move according to the dynamics of Newtonian dynamics. That means free flight, elastic collision, well defined. As long as you have finite linearity particles, it's well defined. If you have infinite linearity particles, then issues of existence of dynamics arise, that you must not have infinite energy coming in from far away in finite time. But let's assume that we don't have that problem. Tag one particle, put a mark on one particle, and try to follow its trajectory. Initial condition is random. Otherwise, everything is deterministic. So this xt is the trajectory of the tagged particle. Try to do anything like that. This is out of reach. This is essentially out of reach. I give you some results, existing results about this, but the lecture will not be about this problem. Just for you to have a complete picture. some results, but very, very so far from satisfactory. Far from satisfactory. Variant, which is much simpler but still infinitely difficult, is the following. Take one tagged particle of radius r, of unit radius, whatever, and ideal gas around. These are point-like particles around. This has mass m, these have mass 1. Give them Gaussian velocities, independent Gaussian velocities with average kinetic energy equal. So this will be Gaussian of variance 1 over m, and this will have Gaussians of velocity 1. The light ones don't know each other. They don't interact. So you have one single particle suspended in ideal gas. Right? And let this move again. So you have these velocities given, and so on. And let this system move. You will have, again, random initial condition, otherwise deterministic dynamics. Call the trajectory of the tagged particle like this, and try to do whatever you can. Right? This is much more simple than the other one, because you don't have interaction between these particles. Nevertheless, you have memory due to recollisions. No one will stop this particle, recollide someone met in the past. It will happen. It will happen. Meet a slow, it happens at some time that a slow particle is met, collided, and some much, much later time recollided. It's a tiny effect, but you can't control it. This is what I say, that well-constructed mathematics will not help here. Alpha mixing, phi mixing, whatever. Now, what's known about this problem, I've worked myself, but not, of course, it didn't start with me, but of course I will speak, not among others, also about my own work on this. So what is known about this, I will not spend much time, even in dimension 1. Even in dimension 1, this is a difficult problem if the masses are different. If the masses are equal in dimension 1, it's an easier problem, because it's geometrically easy to construct. I will not go into details. But if the masses are not equal, even dimension 1 is a far non-trivial problem to prove anything. What we know is back in a paper by Sinai and Soloveichik, and another paper, these appear back to back, of myself and at that time, my PhD advisor, back in 1986, I think. We prove bounds on the limiting variance, nothing else, just bounds on the limiting variance, lower and upper bounds on the limiting variance. That means that the variance of the translated particle divided by t is bounded from above and below by two constants, actually independent of any interesting result. Nothing more is known for the general case. In another scaling limit, when you let in the limit m increase, so not only m equals some m times capital T, like that. So you take the diffusive scaling, but at the same time you rescale the mass of the particle, of the heavy particle. Now this started with the work of Richard Holley, back in 71, I think. And then a later page that's in one dimension. And in higher dimension, there is a paper of Leibowitz and Dürr and others, where they prove under this limit, mind, it's scaling, diffusive scaling, but the particle is made ultra heavy at the same time, right? The process will converge to an Ornstein-Uhlenbeck. I mean, the velocity process will converge to an Ornstein-Uhlenbeck process, and the displacement will converge to an integrated Ornstein-Uhlenbeck process. Very difficult and very, 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 very interesting thing. Later, we have a similar result with light, let me not go. There is another result when the scaling of the mass is not that strong, is slightly between fixed mass, and that one I will not give details. So there are some results on that. More recently, last year Saint-Flour was about, one of the lectures in Saint-Flour last year was by Thierry Bodinot. So Bodinot and others. And Saint-Flour lectures in 17. He takes this, or they take, is Laure, Saint-Raymond, and Bodinot, I think. Laure, Saint-Raymond, and Bodinot. They take this problem, but in the dilute limit. I will speak later about a similar problem in another context. Dilute limit, that means not only take this scaling, but take low density, very low density of particles. And okay, it's a more complicated, complex thing. I'm not able to tell you here in the spot because it's too long to introduce notation for it. But in a particular dilute limit, this problem is done. This problem is done by Saint Laurent and Bodinot, and there were these lectures. Okay, so this is one, and the most difficult one. I will not speak about this problem anymore. Just I wanted you to know that there are really terribly heavy and terribly difficult problems here, which are 100 years old, I could say, and worth spending some time on that. A second example, I go to the easier example, but still, second example is the Lorentz gas. The random Lorentz gas, not periodic, but random. The random Lorentz gas means the following. Put down scatterers on RD. Put down spherical scatterers. They can overlap now if you wish, of equal radii, according to a Poisson point process of intensity rho. Let the radius be r, right? Assume that rho times r to the d is small enough. If rho times I to the d is small enough, then you have positive probability to not be trapped. Right? Now, due to a very simple percolation argument, start a particle from the origin, assuming origin is not covered by a scatterer, with random unit velocity, randomly oriented unit velocity, and let it move according to the rules of to Newtonian dynamics, right? And denote xt, the trajectory of this particle. Again, initial condition is random, dynamics is fully deterministic. Can you do anything like this? Now, what is known here, old and new, and about this, if I have time left at the end of the second week, I will speak about this possibly. What is old is the Boltzmann-Grad limit. The Boltzmann-Grad limit is the following. Let rho go to infinity and r go to 0 jointly, so that rho times r to the d minus 1, say, stays a constant, or goes to a constant. So this picture is the density is increased by the radii are smaller, are very small. Now, if you do it that way, then you easily convince yourself that the free flight paths stay of order 1. Right? And it is proved by Galavotti and Herbert Spohn, Giovanni Galavotti and Herbert. These are different. So Galavotti in 19, these are old stuff. I don't remember now, 70, around 70, around. And Herbert Spohn, that's about 10 years later, I think it was 78. And there is also a paper by Sinai and, Bunimovic, Boldregini, Bunimovic, Sinai. I don't write it down because it's too long to write down. Boldregini, Bunimovic, Sinai later in the 80s. Various versions of what I'm saying is proof that in this limit, x of t, the process x of t, in the Boltzmann-Grad limit, so I should put here the parameters rho and r. In the Boltzmann-Grad limit, this converges to a simple object, not Brownian motion, but a simple object, yt, where yt is a Markovian flight process. So take exponential length flights, change velocity according to a Markovian kernel of change of velocity, another exponential, and so on and so on. It doesn't look that difficult, but it's difficult to prove because again, you have to control recollisions, you have to control memory. Same problem, have to control memory. And after, if you have that one, then in a second step, of course, it's trivial in a second step to prove ytt by square root of t converges to a Brownian motion, because this is essentially a random walk. But going from the memory process with the memory to the random walk is a non-trivial thing. So this is old. What is new here is a recent result I have with a PhD student in Bristol with Chris Lutzko and myself, is the following. Take the Boltzmann-Grad limit. This is a fine difference, and here you will understand difficulties. Take the Boltzmann-Grad limit, so rho, the same, the Boltzmann-Grad limit, this one, but at the same time, take t equals tr equals r to the minus 2. Here I have to add an epsilon. So mind, this was done with Boltzmann-Grad limit with a finite time horizon, and then proof for this process. This is a trivial step. This is, and then what I say is that xt rt by square root of t converges to Brownian motion. So this is a much more difficult thing, because here you don't see, the longer the time horizon is, the more recollisions you see, the more memory you have. Yeah? The Holy Grail here, the Holy Grail would be to go up with this exponent to infinity, which we are not able to do. Right? So this is a second example. If I have time left, then I will show some elements of this statement, which is nice. I skip one example because time is, maybe I don't skip, but I don't give pictures. Now we go, so far we had random initial conditions and deterministic dynamics. Now the examples coming will have some randomness in the dynamics, right? There is the Takt particle motion in interacting particle systems, and I think I will skip that one because time is indeed running very, very fast. So there is another, which is back in the 80s, there was a lot of work on that, Varadhan and people around Varadhan. Maybe I speak about it because anyway I want to refer to that work of Varadhan. So Takt particle, so that's example 3. Takt particle in interacting particles in stochastic interacting particle system. And I give as an example the simple exclusion. the simple exclusion process, which many of you, hands up, who knows well what the simple exclusion process is. Hands highly up. Highly, highly, highly. So less than half. So then I tell you what the simple exclusion process is. Take the lattice ZD. So this is ZD. And you allow 0 or 1 particle per site, at most 1 particle per site is allowed. A configuration consists of particles placed on the sites, but you don't allow more than 1. You have empty sites, and it looks like a percolation picture, but it doesn't have anything to do with percolation, right? Now, particles try to perform random walk. Particles do random walk, namely there is a kernel, a random walk. So P, Z, Z in ZD, this is a random walk kernel. It could be just nearest neighbors, symmetric random walk. It's a random walker. Everybody understands what I mean by that. And particles, independently of one another, try to perform these steps. So let's, in continuous time, sorry. Continuous time, so think about the p's as rates. And when the clock rings, then the particle tries to jump, say, a jump in this direction was attempted. But this is not allowed, because it would jump on the top of another one. So particles, in continuous time and independently of one another, with these rates, try to jump to from x to x plus z. And those jumps, which would result in a forbidden configuration, are suppressed. Otherwise, and this is the dynamics. It makes sense. One can write down explicitly infinitesimal generator and so on. So it's a very, the state space of the Markov process is 0, 1 to the, what is that? 0, 1 to the ZD is a compact state space, so you can write down things explicitly. But it's a complicated object. Right? Now tag 1 particle. So this was just to illustrate what the dynamics was. Now if a jump on that direction the particle is instructed to do a jump, then it will be performed because there is no obstruction here. Right? Now tag 1 particle, this was a special one which has a mark on it, and follow its trajectory. Dynamics makes sense. I forgot to tell you, but I tell you now, it's well understood. So if you look from outside to the system, then all Bernoullis, all IID configurations with density rho, whatever rho between 0 and 1, are stationary and ergodic for this dynamics. So fix a rho, start with stationary distribution, and follow the trajectory of a tagged particle. It's clear it tries to be a random walk, but it has to interact with the others. And it's not quite a random walk. Now here the results, these go back to the 80s, 90s, and early 2000s, and Varadhan is the first name to be mentioned here. When Pz is P minus Z, that means the random walk, basic random walk is symmetric. Assume finite range. Assume finite range. I don't want to enter into problems with long tails and heavy tails and finite range. If it's symmetric, so this is the simple symmetric exclusion process, right? So this was done in a paper by Kipnis, by Claude Kipnis and Varadhan. In 1986, and this is a very important paper in my story because the famous Kipnis-Varadhan theorem, which many of you have heard about, or hope so at least, namely martingale approximations and proving central limit theorem through martingale approximation, and these lectures will be about that type of topics, appears in this paper. And they prove, so indeed, invariance principle proved. Except for the one-dimensional case with nearest neighbor. If it's one-dimensional and only nearest neighbor jumps are allowed, so symmetric nearest neighbor, then something special happens due to particles being confined on the one-dimensional lattice, and then it's not diffusive, then it's subdiffusive for some reason, but it's a different type of problem. Otherwise, in more than one dimension or in one dimension in non-nearest neighbor interactions, it's done. And this is based on the Kipnis-Varadhan-Martingale approximation you will hear about, because it's not only for this problem, but it's something very, very important. If Pz, if sum of z, so this is one case. The second case, I'm still in this example. If sum of z, Pz is 0, according to z, we assume it's finite range. I don't want to go to beyond finite range, but I don't assume symmetry. I just assume zero mean. Then Kipnis-Varadhan as it is doesn't apply. By the way, it's very, very, very important, and one of the main message I want to push through. In Kipnis-Varadhan and in this problem, it's essential that the background, that the Markov process in the background is reversible. All operators appearing naturally there are self-adjoint in over the Hilbert space. I will be much more concrete than this later. And spectral theory works, and the reversibility is terribly important. In Asaf's lectures, all random walks are reversible. In these electric network setup, random walks are reversible. And combinatorialists love random walks which are reversible, but in real physics, not all random walks are reversible. So in particular, this one is, but this one is not. And the Kipnis-Varadhan theorem doesn't work, but a variant, so there is I just drop terms here, but I will be concrete about them later. So Kipnis-Varadhan extended to non-reversible, but with something which I just give a name now, but later I will tell you what it is, strong sector condition. Strong sector condition, don't care about it now because later you will understand. These sector conditions will be very important in my lectures. This means that the operators which arise here as infinitesimal generator of your Markov process have a self-adjoint and a non-self-adjoint part. You decompose it to self-adjoint. And a sector condition always means something that the self-adjoint part controls the non-self-adjoint part in a sense. But these are very, very subtle functional analytic things, which will come up. Right? So the strong sector condition is used or invented or proved by, this is done only by Varadhan. So this is Varadhan. Sometime, let me not go to my notes, sometime in the late 90s, 97 or something like that. With question mark, I don't remember. And the last in this series of simple exclusion things, of course, you may not assume even this thing. You may say that you are looking at the simple exclusion process based on a walk with a drift. Now, if there is a drift, then this strong sector condition doesn't work anymore. It's very strongly non-symmetric or non-reversible. And something else is invented in a paper by, again, Varadhan and Yao and Sethuraman, Varadhan and Yao, where they prove a weaker condition, that means a stronger theorem, which they call graded sector condition. I will come to that. I don't go into detail now. Another sector condition, which is the condition is weaker than this one, and they prove in 3 and more dimension for the general one, when Z, P, Z, not necessarily 0. So that's done in this paper by Sethuraman, Varadhan, and Yao, 2000, 2001, something around that. And the graded sector condition is done there. Message, when you don't have self-adjointness, then you have to do something else. And then there is no spectral analysis. You have to go to other tricks, and that will be an important technical message of my lectures. Let me go to my examples now. This so far, okay, this was my example, in a sense, but the lectures will concentrate on theoretical parts related to these functional analytic things and application. Yeah. When I say z, I mean jump rate from x to x plus z. So spatially, my models are spatially homogeneous. I don't do no, and I'm down in d dimensions. D dimensions, homogeneous, but long memory due to something. Right? Question, yes? Question? Yeah? Just loudly to have every.
The initial particles, is that manifest somehow in the diffusion coefficient of the limit?
Say it again. That.
Just the density of the particles.
That will, yes, certainly it will influence. So the diffusion, there is no closed formula for the diffusion coefficient. And the fact that the diffusion coefficient is a continuous function of rho, even an analytic function of rho, these are very, very subtle things. But indeed, it depends on the density. Yes, yes. Yeah. Now, my fourth example, and this will be my central object of fourth example, is random walk in random environment, a particular kind of random walk in random environment. Random walk in random environment. Now, this is such a topic since the late 70s or early, maybe late 70s. This is one of the central topics in modern probability theory. Take random walk on a lattice ZD, where the jump probabilities are not homogeneous. I mean, homogeneous in the micro picture, but homogeneous in the sense that are translationally invariant created, but randomly. The jump probabilities, so take ZD, so this is ZD again, and the jump, I have to introduce a little bit notation. I will denote by E. I will only speak in this context in nearest neighbor. I could go further, but I don't want. Is the neighbors, is those, say, K in ZD with K equals 1. So these are the possible jumps, right? I have now, forget about that PZ. You asked me whether the PZs are constant. There it was. Now the PZs are what is P. So let's P, how should I put it? P, K, X, K in E, X in ZD. These are my jump rates. So that's the jump rate, the rate of jump from X to X plus K, right? So the probability, I will speak about continuous time random walk, it's more convenient for me. Sometimes they are equivalent. This anyway is more general than the discrete time. So X t plus dt equals K X plus K given X t equals X is P sub K at X. This is just a random walk. I didn't speak about randomness yet. And by, of course, I mean that the process is Markovian. So all past is there. Now, we speak about random walk in random environment if these guys are random variables. A translation invariant ergodic translation invariant in X and ergodic in X. Random variables could be independent, could be not, right? Now, this is such a huge question that we don't know much about it. We don't know much about it. We know a lot, but not enough. My object will be okay. My object will be the bistochastic or doubly stochastic. The doubly stochastic, which means that for any x sum over k of P sub kx is equal to sum over k of P sub minus k x plus k. So the sum of the jump rates coming inwards to any site equal to the sum of the jump rates going outwards. Yeah? I don't say this is 1 because I want to keep it a bit more general. Right? In particular, random walk among random conductances, which is much, much studied, is there. Right? Random walk among random conductances is there. I mean the continuous time version. And again, the message is, my message will be, but preliminary message is, but this is not self-adjoint. As opposed to random walk among random conductances, this won't be self-adjoint. So my problem is, so I think about, my problem is take this type of thing, ergodic, random ergodic, and look at the random walk among random, not random conductors, random walk with this thing. And try to prove central limit theorem. I stop a little bit because I want to give motivation for this problem. Is not just that I want to go beyond random walking, random conductances. It's more than that. It's in principle an important thing. Before I, let's see what's better for me. Better for me if I give you examples of this, and better for you. Maybe not better for me, because you will think about the examples and not pay attention to what I'm saying later. Here are the maps of 3 cities. 3 two-dimensional cities. You will not see much difference at the moment. If I give you just a Google map without one-way streets, you don't see the difference. And the city council decides in all these 3 cities decide to make some streets, or to make the streets one way, or some streets one way, or maybe all streets one way. This is a democratic. They do the following. The mayor sends out a letter to each block. These are blocks. And each block, the people living in each block can decide themselves which way they want, the streets around the block, which way they want it one way. They want it this way, one way, this way, these guys want it that way, this one that way. They decide independently, say, of one another. And this is the decision which the council gets. Now they say, okay, this is the decision. When there is consensus, here there is consensus, then we make it one way that way. Where there is consensus here, we make it one way. There is no consensus there, we leave it 2 ways. We don't know what happened there. There is no consensus here, there is consensus there, and there, and so on. Let me not waste time with this. Now, if you do this picture, you will realize that at each single corner, the same number of one-way streets come in and go out. Yeah, do it. So you see, there in this case, for example, we will have 2 out and 2 in at this corner, and so on. Play with it. There will be some corners where there is no one-way street. Either you have 1 in, 1 out, or 0, and so on, right? And the council decides, okay, these will be our one-way streets. And now you are the driver in the street. Start with your car. Whenever you arrive, whenever you have a choice, you choose with equal probability. And when you don't have a choice, then you go the way it's given. and you drive like that in this city like mad, how far you get? How far you get in time t? Is it clear what I'm saying? Is the driver driving? Drives, otherwise, so always whenever there is a choice, tosses a coin or chooses at random with equal probability, otherwise when it's determined. Certainly, there is some memory here because it's a random walk in a random environment. It's a random walk in a random environment. Now this is Manhattan. This is Manhattan, and here it is decided for the streets and avenues all together, but randomly. You understand what I mean? And the streets equal, same with the streets. You understand what I did? I tossed the coin at every single street and avenue, and I decided what way to make it one way. Now you are a driver in this street. This is somewhat simpler because here at each single corner, 2 in, 2 out. You have a coin in your pocket. You are the driver. Whenever you arrive to a corner, you toss a coin to decide which way to continue. You have 2 choices. How far you get? How far you get in time t? Do you get? When I ask how far you get, I ask whether xt is diffusive, divided by square root of t, converges to a normal, or not, or something else, or bigger than square root of t, or smaller than square root of t. Who knows? And here is the most difficult one. Now here, the mayor, this person was a physicist at his young age. At his young age, this guy was a physicist, and he learned about either the 6-vertex or the dimer model. Who knows about the dimer or the 6-vertex? Hands up who knows the 6-vertex model, or square eyes. Hands highly up. Some. And about dimer models? It's strange. There is some overlap. Good. Anyway, let's choose the 6-vertex model. The 6-vertex model is the following, or square eyes. Is one of the most exciting objects in 2-dimensional statistical physics, actually, or this lattice-based statistical physics. We have to orient each single edge. So the allowed configurations are orientations of each single edge in such a way that at each single corner you have 2 in and 2 out. This is a particular case, but there are more than that, right? I will not waste much time with this. For example, you start with that. And so on. I hope I didn't make a mistake. There is a way to do that. And not only one way to do that. If you take a box of size n by n, there is exponential in n squared ways of doing that. That's the famous result of Elliott-Leib back in the 60s. So you can take a random in the limit. You can take. So just trust me that in the infinitely extended case, there is a canonical measure distribution of arrows like that. And by the way, you can do it in higher dimension too. But in 3 dimensions, you will have 3 in and 3 out, rather than 2 in and 2 out, and you would call it 6 choose 3. How much makes 6 choose 3? I don't know. Anyway, it's not 6 vertex, but something else. But 6 choose 3 vertex model. Anyway, so this is another way of deciding about one-way streets, and the mayor of this city decided to do it like that. And now you are a driver in this street, and you drive like mad. You have a coin in your pocket, and you toss the coin at every single corner, decide where to go, which way to choose. It's very easy to check that you are not trapped. You are never trapped, right? And question, how does it scale? Okay, I hope I didn't lose my audience now with these problems. I will not tell you till the end of the week maybe what happens here. But some of you, of course, may guess. And, but these are motivating examples for this. These are all of this kind of doubly stochastic random walks in random environment, very simple to formulate ones. I just wanted to give you examples that it's interesting. It's not only that let's make a little bit more difficult mathematics. It's interesting. Another reason, not unrelated to these pictures and why it's interesting, is the following. Let me write down the diffusion problem, the corresponding diffusion problem, corresponding to this one. The corresponding diffusion problem, or slightly simplified, I don't want to go into the most general case. The corresponding diffusion problem will be dxt equals dbt plus vxt dt. Of course, this is just a diffusion in Rd, where x Vx is stationary ergodic vector field, which is almost surely divergence free. So double stochasticity, in a sense, corresponds to divergence free, to drifting in divergence free vector field. You will see, I will speak a lot about this. You can't see what I'm writing. Can you read my handwriting, by the way? Yeah. Now, if I put it that way, then those of you who know a little bit of physics will realize that divergence-free, this is a condition of divergence-freeness of the flow. I will use the term flow slightly differently than Asaf used it. I will say divergence-free flow when it's divergence-free. You call flow a divergence-free flow. So this condition is divergence-free. Sourcelessness. Sourceless flow. So this is a sourcelessness condition like that. Now, as you know from, or some of you may know from physics, divergence-free flow means incompressible flow. And so this models, in a sense, drifting in incompressible turbulent flow. It's a model for drifting of a particle in incompressible turbulent flow. So that's the physical motivation why this is interesting. And the lattice version is a lattice version of that, right? I have another mathematical reason why this is very interesting, but I will tell you later when I come concretely to this. Okay, now what are the results here? I have to make some assumptions. The results are the following. So it's an open question. As I told you, it's an open question. I tell you from start, this will be diffusive. This will be diffusive. That means the divided by square root of t, divided by square root of t will converge to Brownian motion. And actually here I made these loops very little local. I could make much more general, but still build up things from some finite loops, translated loops, randomly translated loops. Again. This will be super diffusive in up to 4 dimensions. In 1 dimension, in 2, 3, and 4 dimensions. In 2 and 3 dimensions. This will be super diffusive in 2 and 3 dimensions, robustly super diffusive in 2 dimensions. That means the power you have to divide to get something, I mean, the variance, the order of the variance is super linear as a power, higher power. I can tell you later what. And in 4 and more dimensions becomes diffusive. And this will be a consequence of a theorem I'm going to tell you. And this guy is marginally super diffusive in 2 dimensions with logarithmic corrections, probably. No proof, but good reason to believe. And diffusive in 3 and more dimensions. Question?
Transients and recurrence?
Transients and I'm not that, okay, transients and recurrence are great questions. When I say I'm not interested, I don't mean I'm not interested. I'm not working on it. Of course, when you have, I think this would be certainly transient. The super diffusive ones will be not transient, sorry, recurrent. This guy in 2 and 3 in 2 dimensions certainly is transient. Maybe there is also some result about it. I don't know. I think it's transient. If I had, how is that? if I had local versions of the central limit theorem rather than global versions, then would help me to prove transience in high dimension. I don't have a strong opinion. Probably the reasonable conjectures are true. I never worked on transience. And so that's, as you said, transience is a combinatorial problem, which is legitimate and fine. I'm more interested in the physically motivated problems which lead more to analytic problems than combinatorial ones. Okay, now what are the results here? And this will be the bulk of my lectures will be about this type of random walk because this is important and the recent and, in my opinion, nice results here. Under some conditions, there are some natural conditions about zero mean, for example, that I don't make more up than down. So I want to exclude trivialities or trivial. So assume under the natural conditions and something more. There is a condition called H-1 condition, which is essentially, I will be concrete about this. H-, it comes from, it's a Sobolev type of condition, which you will see later. I'm not going to give the technical things now. It's a condition on correlations of the drift field. If it's a subtle thing because it's formulated in terms of Fourier transform, so there is no one-to-one translation, but in vague terms, if you have sufficiently fast decay of correlations of the drift field, and fast means faster than in some power law, which you could compute dimension-dependent power law, but this is not a one-to-one. The proper condition is formulated in Fourier terms, and that's why I'm not giving to you now. So under the H-1 condition, there is a fresh theorem by Gadi, Kozma, and myself. This is 1917, and you find the paper in the lecture notes published last year. When we prove under the H-1 condition, we prove the annealed central limit theorem. When I say central limit theorem, I mean all finite dimensional marginal distributions, not only one dimensional marginal distributions. But I don't say invariance principle because we didn't prove tightness of the process, which is just, okay, could be done, but we haven't done it. And by annealed, I mean improbability with respect to the environment. Actually, I will be very concrete about this because it's halfway between annealed and quenched. And I have a more recent paper which will appear soon in the Annals of Probability, which is the quenched result under slightly stronger condition than that. So as you will see, this is a sort of L2 square integrability condition of something, some covariances. And I will need here, instead of L2 and L2 plus epsilon for some reason, but the quenched result is there. So my main body of my talks will, when about applications, will be about these two things. And the technical ingredients to be used, to be employed, will be various sector conditions which beyond Varadhan. So there is another one which I will tell you, which includes all these, which I mentioned, the Varadhan sector conditions, and it's neat. So functional analytic sector conditions, and in order to prove, and other tricks, in order to prove the quenched, what you will see, and I'm happy to include that in the lecture, classical things, Nash inequalities, and Nash moment bounds, hence highly up who know Nash inequalities. Hence highly, I know at least one or two people in the lecture room who know Nash inequality well, but I don't see one. I see one hand. Okay, there will be Nash inequality and Nash moment bound extended, a new variant which is stronger, and I'm happy to speak about that because that's classical. That's a message you can take indeed home. Nash inequality is something worth learning.
So this condition only applies for the democracy example?
No. Yeah. This condition applies, okay, for the democracy actually much more applies. So the democracy is a baby. Democracy is a baby version of organizing society, right? It applies to this guy in four dimensions, but not in 1 and 2. And it applies to the to the square ice model in 3 and more, but not in 2. And this is related for those of you who know these tightness, okay, the last one, tightness of the height function in various two-dimensional models is very closely related to that one. So that's H minus 1, just for those of you who like this two-dimensional height function business of when height functions are confined or tight or not and so on. That's related to that problem. Yes. I still have 20 minutes, which is very, very good for me, because there is another example I want to mention. Or another class of examples. By the way, I also plan to speak about super diffusive limits when H minus 1 doesn't hold. So when H minus 1, I didn't mention this, you'll find some papers there towards the end of my note. When H minus 1 doesn't work, then you expect to have super diffusive behavior. And in some cases, we are able to prove super diffusive lower bounds, which means that indeed, which don't match, unfortunately, the conjectured order of super diffusivity, but nevertheless are super diffusive and are informative. And let's go to a fifth example, and I will do it in continuum because it's easier to speak about continuous space than about diffusion than about random walk version, but it's also for random walks. So fifth example, self-repelling Brownian polymer. I didn't give the name, so I don't take responsibility for it. Or it's related to so-called true self-avoiding random walk on the lattice. What is called true self-avoiding random walk, which is missed. The names are not good, but you will see what I mean. Let me speak about it. So okay, I start with a function. Vx will be just a smoothing function, r d to r, plus positive, say, is an approximate identity. Approximate identity, that means it integrates to one. Let's say its Fourier transform, I need its Fourier transform is positive. Take as a concrete example in mind v of x be e to the minus x squared. Something like that, an approximate delta. I need in my setup an approximate delta. You will see in a moment why. And I look at the following process. I am in Rd, dxt equals dbt minus, I write down, you will see some symbols to be defined, to be explained, minus gradient of v convolved with Lt at xt dt, where Lt is the occupation time measure so the time spent in, let's say, A is whatever open set or measurable set, whatever. So I have a process which is defined by a diffusion equation. Lt is its own occupation time measure, convolve the occupation time measure with this approximate identity, because otherwise you have a very wild object. Take the negative gradient. So the physics is the following, that the process is pushed away from places more visited in the past. It's pushed away in the direction of negative, in the negative gradient direction of the local time. Okay, if you want to take away this, think about V as a delta, but it doesn't make sense. Even in one dimension, it doesn't make sense if you take away the V, right? So it's a very wide object. That's why I convolve it with a V. There are other ways of writing now. It's not difficult to show that this is not a stochastic differential equation, but something of the sort, stochastic integral differential equation. It has a unique, strong solution. I didn't say about V, it's infinitely smooth. V is that. Take V like that, right? So what happens here is that I have a process which has a randomness, has a white noise randomness in it, but it's pushed away from places much visited in the past. It prefers to go to other places. How does it behave? Again, the question is the same. Does it behave diffusively in the long time or not? You can do it on the lattice. Take it on the lattice. Take a lattice walk, which is somehow the rules of jump are determined, and there are papers about this, are determined by the occupation time measure, occupation time of the lattice sites, and it's more likely to jump to a neighbor which was less occupied in the past. It's negatively, or if it makes sense, negatively reinforced. So discouraged. I don't know what is the negation of reinforcement, discouragement. Discouraged random walk. Good? And the question is the same. Now, of course, you guess that you expect something like super diffusivity, faster diffusion, no? That's not normal to expect faster diffusion. Actually, my work in this story started back in the 90s, and I had papers. There are many conjectures I will tell you about this. Okay, I tell you what the conjectures. This sort of problem appeared in physics and mathematics literature sort of parallelly without information of each other in the 80s. There are the physics paper by people working in quantum field theory who wanted to understand long memory behavior. And there are mathematics or probability papers by Rick Durrett and others about 5 years later maybe, but they didn't know about each other. And the physics conjecture was that in dimension one, you expect xt to behave like t to the 2/3, so be strongly superdiffusive. Now, I have papers about that back in the 90s. The lattice version, which I will not speak about now because it takes too much time, but made it precise. These are conjectures. In d equals 2 xt, okay, say xt squared, something like t times log t to some power. So it's marginally superdiffusive. And in D3 and more, you expect, or it is expected that the central limit theorem holds. So these are the conjectures dating back, if you look at these mostly physics papers, but also mathematics papers. And what is done here is that, okay, in particular cases, in particular lattice cases, this is settled. We have lower bounds. We don't get this much. We get log t lower bound here, but nevertheless, it's a superdiffusive lower bound in 2 dimensions. And in 3 and more dimensions, we prove the central limit theorem using these sector conditions I'm going to tell you. So these are various kinds of problems I will measure. I don't exactly know how much time I'm left. Do I have 10 more minutes now? What is the time to finish? I don't remember. 15 minutes, good. 15 minutes, perfect. Good. Now, what is the general approach I'm going to tell you? I'm not doing any technical thing today, of course. Tomorrow we start with technicalities. But I give you the idea how we start. I will okay, I gave you many examples, and the technical approach I'm going to expose now is working for those with random dynamics, not with the deterministic Newtonian dynamics. That's a different kind of story. The same problem. If you are far away, enough far away, then you see that the problem is the same. So deriving diffusive scaling limit or other type of scaling limit in relevant problems with long memory. But in the deterministic cases, the techniques are totally different. So what I'm going to tell you now, this approach, which I'm going to sketch now, is working in the last 3 examples. So it will be a little bit philosophical, but it will get very concrete mathematical content soon. So what we have, so the general approach is the following. We have a process x t maps to xt, but not only xt, but there is a background with which my process interacts. In the random walking random environment, the background is just there and not moving. But in the other cases, for example, in the last case, the background will be this local time profile or gradient of local time profile, which changes in time. So let me just abstractly call it beta t. So this is the displacement, and this is the background. And this is a Markov process in Rd times some space which I don't specify now, omega. Typically, omega is an infinite dimensional function space. For example, if this, in the last example, this is the local time profile, it's a function. It's a function. It's element of a function space. So we have to be careful about what this space is, and there will be fine analysis here. So this is the process as seen from outside. You are observing the displacement and what happens with the environment, right? Where beta t, let's say, let me be concrete. So beta t typically is beta t and x. So I wrote only beta t there, but this is what I said. It's a function of x. So beta t is beta t and x in R d. It's a function, right? For example, the occupation time measure or the environment. If it's the environment, then it doesn't depend on t. It's fixed. In a random walking random environment, what was it? In the interacting particle system is all the other particles moving around. Yeah, we will see concretely. Now, given that, a standard and very natural thing to do is to travel with the random walker. This is looked from outside. The system is seen by a outside fixed observer. It's very natural to travel with the random walker and to observe the environment from the position of the random walker, and that's what we will do. So I will define a process eta t equals eta t and x in R d, such that eta t and x is typically beta t of x plus xt, if I'm not mistaken. X plus xt or x minus xt. Okay, you correct me if it's wrong. So you observe it from the... Is it plus or minus? I'm tired now. Anyway, so you put the origin at xt. You put your, probably it's plus. It's correct now? Good, let's leave it there. Okay, so this is the environment as seen by the random walker. And what happens, this is not a rule, but in lucky cases, that t maps to eta t will be itself a Markov process. A Markov process on some, let me say this is an omega dash, because I don't want to carry the dash with me, on omega. This might be slightly different because, for example, in the interacting particle systems, if you travel with your random walker, then the origin is never occupied by another particle because the origin is occupied by the particle you follow, right? So there might be a slight difference here. So what happens is that this is a Markov process itself, and typically this space is an infinite dimensional function space with some measure on it. So actually, what happens is that this process encodes a lot of information. We trade. Here we have a finite dimensional process with long memory. We trade it for an infinite dimensional process which is Markovian, right? Okay, so that's what happens. And this will be stationary, so omega pi. Pi will be a measure with respect to which this process will be stationary and ergodic, right? And what we do is the following. We subtract. We will have something like expected value, conditional expectation of the infinitesimal displacement given ft. Ft is the sigma algebra generated up to time t by jointly everything, right? This will be a function of eta t dt, where typically this function will be in L2 of that space, where phi will be in L2 of omega pi. Is it clear? So I subtract what probably you would call it compensator or something like that. So I want to make a martingale. What I do is the following. I write xt equals xt minus integral from 0 to t of phi eta s ds plus integral from 0 to t of phi eta s ds. Of course, it's not a big deal to write that. But what matters is that this guy here is a martingale, because that's how I constructed it. I subtracted the infinitesimally, I subtracted the conditional expectation of the increment, right? So I make it a martingale. Actually, it will be a martingale with an L2 martingale with stationary and ergodic increments. So for this guy, I know everything. I know the martingale central limit theorem, the martingale invariance principle, which applies for martingales with ergodic increments. No problem. So all difficulty is encoded in this integral. So here is the question now, which looks like a very, very naive, simple question. If you look naively at it, then it looks naive. Here is the question. We have eta t is an ergodic Markov process on omega pi. By ergodic, I mean stationary and ergodic Markov process on omega pi. Right? It has some infinitesimal generator you have to write down and so on, so there is some analysis behind. There is a function phi which is in L2 omega pi, which is zero mean. Right? And now you ask about integrate along the trajectory, divide by square root of t, let's say integrate to capital T, divide by square root of t. Is there a central limit theorem for this guy? Just additive, add the value of the function along the trajectory of an ergodic Markov chain, right? And of course, as you did probability 1, probability 2, you proved something like that for Markov chains, didn't you? By the way, who could prove who could give me an idea, how would you? Indeed, it is the case. There is a central limit theorem if my Markov chain is a finite state space. If this is a finite Markov chain, then this central limit theorem holds, a central limit theorem holds for that, and there is, in principle, very simple proof, though if you want to write down the details, it will take you a couple of pages. Who could tell me an idea? How would you prove a central limit theorem for a finite state space Markov chain, like that? Let eta be a Markov chain on a finite state space, phi, a zero mean function, zero mean with respect to the stationary ergodic measure. How would you prove? Ah, come on. I want a brave one person to tell me. Okay, help me. Exactly. That's it. So that's the best way of us, the most instructive way to do it. Do excursions. Name one of the sites, your origin, and decompose the trajectory to excursions. And when you write down all the proof, and of course the excursions are independent, all whatever happens with the excursions are independent, so you will have sums of independent identically distributed objects, just you have some garbage at the beginning and some garbage at the end, which you have to control. And you don't have a deterministic number of summons because the number of excursions you do in time t is random. So when you put together all these arguments, it becomes longish, not only longish, but you have to do very, very careful estimates of the decay tails of recurrence times and so on, which are of course exponential in finite case. Anyway, this works. But when you are beyond the countable, when you go beyond the countable, then this doesn't work, of course. Then you don't have anything like that. You don't have recurrences, you don't have anything. So you have to do something totally different. And proving or disproving central limit theorem or diffusivity, proving diffusive bounds, proving martingale approximation for this type of things, that will be one of the technical, main technical contents of my lectures. How to do that. That's what I call Kipnis-Varadhan theory, because it started with the paper of Kipnis and Varadhan. There were these later paper of Varadhan and sometimes collaborators. I have myself a paper back in the 80s about that, because in the 80s I was obsessed by going beyond reversibility. Because Kipnis-Varadhan was for reversible. So doing that for general as you can cases, that will be one of my technical messages. And should I give you some homework? Yes, homework. Work out the central limit theorem for 3 states. 2 is too simple. If you do it for 2 states, that's too simple indeed. But for 3 states, okay, I'm joking because you will not be, okay, you will be able to do it, but it takes more time than what you are having in the afternoons. But think about it. Think about it. How would you prove the principal steps of proving a central limit theorem for that in the case of finite Markov chains? And you will realize that this cannot be saved to infinite dimensional Markov chains. Okay, so thank you very much, and we continue tomorrow.